Okay, so now that we've looked at games and their equilibria, let's look more closely at the special class of zero-sum games. To begin with, let's remind ourselves of what they are. They are two-player games, specifically, where the sum of the players' payoffs is zero, and we've seen the two canonical examples. We've seen matching pennies, and we've seen rock, paper, scissors. And we also said that, in fact, zero is not particularly privileged, that any constant would do, and perhaps more proper name would be constant sum games. So what can we say about them? Well, we could reason about them as games with no special consideration to the zero-sum property. But if we look carefully, we see that we can actually say the following about them. This is called the Minimax theorem, and let's see what it says. It says that we can look at each of the players in turn and reason about what they might do in equilibrium. So in particular, let's look at what it says about player one. It says that player one's strategy S1, if in equilibrium, must be the results of doing this optimization on the part of player one. And what did it say? Player one says to itself, well, I care about my payoff, my utility. And I want to find an S1 that maximizes my utility, that's the argmax part, knowing that my opponent will do everything they can to minimize my utility. This is where we're using the zero-sum property of the game. That makes a lot of sense. And similarly, we can look at player two. Player two says, well, I care about my payoff, but my payoff is minus the payoff of my opponent. And so therefore, what I want to do is to find the argument that will minimize that payoff to the opponent, knowing that the opponent will do everything they can to maximize it. And so what that really means is that the equilibrium strategy is the max-min of this value, or if you wish, also the min-max of this value. So this is called the min-max theorem, and you can view it as describing what the equilibrium is. So here again is matching pennies, and now we look at this three-dimensional surface, which is all the payoffs to the first agent, and therefore minus the payoff to the second agent, given any strategy they might pick. So for example, if we look at this point right here, at this point, both players are playing heads with probability 0. And so therefore the first player wins and gets 1. On the other hand here, the first player is playing heads with probability 1, and the second player is playing it with probability 0. They're in mismatch, and therefore the payoff to the second agent is maximal. If you look at the space, there's one privileged point here that is, even visually speaking, stable, and it's this location here. In fact, it's called the saddle point. It has a special property where neither player has incentive to deviate. This is where they play, if you project it down, it's where they randomize half-half. If the first player decides to deviate, then what will happen? Then their payoff will only go down, and they wouldn't do that. Whereas if the second player decides to deviate, then the first player's payoff will go up, and therefore the second player wouldn't want to deviate either. And so this is a pictorial description of the equilibrium point in the zero-sum game. But besides thinking about the max-min as a description of what the equilibrium point, we can actually use it to compute the equilibrium point. Of course, we already have one method for computing equilibrium in all games, and in particular in zero-sum games, but now we have a special point, a new special way of doing it. Let's look at this in the context of a new game, a game that describes a penalty kicking situation. So imagine a soccer situation where there's a free penalty. The kicker can choose to aim to the right or the left, and the goalie can choose to jump to the right or the left. And depending on the choices, here's the probability of the kicker scoring a goal. For example, if the kicker decides to kick to the right and the goalie happens to jump left, then the probability of the kicker making the goal is very high, 0.9. A similar situation happens if they misalign in this way, but perhaps here maybe the goalie is more adept at catching goals on the right, and so the probability is still high, but not as high. If, on the other hand, the kicker kicks left and the goalie kicks left, the probabilities are something like this. The kicker still has a chance of scoring a goal because, after all, it's very hard to catch a penalty, but not nearly as high. So this is the game we're playing, and now let's assume that the payoff is simply the probability. The payoff for the kicker is the probability of making the goal, and the payoff to the goalie is minus that, the probability of the kicker not making the goal. And remember again that in a zero-sum game, 0 is not important, so the sum here will be 1 rather than 0, but as we said, this is not the issue. So how do we reason about this game? How do we reason about the fact that the kicker is trying to maximize his minimum and the goalie is trying to minimize the kicker's maximum? And if we do the two together, then we get the equilibrium. So let's think about it first from the kicker's point of view. Here is the expression that the kicker is trying to max min. We have his strategy S1 and the strategy of the goalie S2, and each strategy confers a certain probability on left or right, some probability between 0 and 1. And if these simply describe the probabilities of ending up in this cell, in which case the payoff to the kicker is 0.6. And each of these four expressions captures the one of the different cells. We sum them up, we get the expected utility of the kicker given the strategies S1 and S2, and now we're trying to max min it. So let's for a moment let's consider his strategy S1 as a constant, a fixed, and let's see what is the minimum that is being optimized by player 2. So we simply copy over that expression from above there. The only difference is we omit the maximization part for now. And now we're copying it over once more over here, and the only thing we do here, we substitute 1 minus S1 and 1 minus S2 for the S2 of R, because of course S2 of R is 1 minus S2 of L, and so we simply make that substitution. Otherwise, we've done nothing so far. We have simply copied things over. And now we just reach out to basic calculus and we say, how do we minimize this function? Well, we take the first derivative with respect to S2L. And again, holding S1L as a constant. And as we know, the derivative of a sum is the sum of the derivatives, so we simply do it in order. For example, let's take this first expression right here. What is the first derivative? Well, we have here, this would simply be 0.6 times S1 of L, right? And what would be the derivative here? Well, we can do this too. The 1 is a constant that will disappear when we take the derivative. And so we have minus SL1, so we'll get, S2L, we'll get minus 0.8 of S1. 1L, and you'll pardon the horrible writing with the stylus here. If we do the same for the other expression and we sum them up, we get this expression right here. And in order to find the minimum, we equate it to 0, and we find out that in fact the S1L is a half, and therefore S1R, which is one minus S1L, is again also a half. This is the equilibrium strategy for the role player, for the kicker. We can now do exactly the same thing for the column player, for the goalie, and find that his strategy will be a quarter, 3/4. And we've now found the equilibrium strategy. The max-min strategy is a half, the min-max strategy is 3/4. This is the equilibrium of this game. One thing you might want to do is now go and verify it. Take the method we know for solving any 2x2 games and just verify that you get exactly the same solution that way.